Hello and welcome back to Calculus 1. This is the part 2, the section 3.7 chain rule. And we're going to take a look at some spicier problems. Last time we talked about the chain rule in the basic form, meaning we had the chain rule, which is the way to take the derivative of a function composition, which is this, right, the function composition. So we will take the derivative of f in respect to g and then multiply by derivative of g in respect to x. So to quickly review, say that we had to take the derivative of, say, 4th root of x squared plus 6. We would first rewrite this so we can see the exponent as x squared plus 6 to the 1/4. And then we would identify that the outer function f is x to the 1/4 and the inner function g is x squared plus 6. So to take the derivative, we regard all of this as one variable. So that would be 1/4 of that x raised to the -3/4, because 1/4 minus 1 is -3/4. Then we copy the inside, which is x squared plus 6. And then we follow with the chain, which is 2x. Now, I did mention last time that you should always simplify, because chapter 4 is coming up. And in chapter 4, this would be just the first step of the problem. Afterwards, you would set it equal to 0 and do more calculations. So we are going to now simplify. 2 and 4 will cancel. We get a 2 over there. And we have x divided by, and we have 2x squared plus 6 raised to the +3/4. And now we can set this equal to 0. We get x equals to 0, and then we move on with our problem. So this was what we did last class. We did some of the trig problems and so on. Today we're going to take a look at combinations of rules, as I promised last time. So now what you have here is the derivative of x squared times sine cubed x. So what type of a problem is this? It's nope.
Polynomial.
There is a polynomial here, okay. First of all, is this chain rule at all? No, good. What is this? Product rule. There's a times over here. This is product rule, and then chain is within the product rule. So if you rewrite this carefully as x squared times sine x cubed, you should see the product rule. Usually we call this u and we call this v. So we need uv prime plus vu prime. Oops, why I put the plus there, I don't know. Vu prime. It's a product rule. And then within this product, when we have to take the derivative of sine cubed, we have a chain. So this is chain within product. So we copy the first, x squared, and now take the derivative of the second, which is 3 sine x squared times cosine x, which is the chain. So the chain rule happens there. Then we have plus our sine cubed x times the derivative of the first, which is 2x. So we did the product rule, and let's make sure this is u, this is v prime, that's v, and this is u prime. And over here we have the chain as well, because the chain rule, you had to differentiate sine cubed. Derivative of sine cubed is 3 sine squared, and that's that. Oh, we're not done. Oops. We are not done because I did not factor. I can kick out x sine squared x, and what's left is 3x cosine x plus 2 sine x. There we go. And now you can set this equal to 0 and get your values and so on for chapter 4. So this problem has a chain rule inside the product rule, and we have to do the product rule first because that will be the rule for the entire problem, and then when we had to take the derivative of sine cubed, that's when the chain rule kicked in. The derivative of, let's say, tangent of x e to the x this would be a standard exam question.
We have tan x. And then we have your product rule is x e to the x.
Good. And that's buried in tangent,
Yes.
which means
Tangent is sine of cosine.
we don't need to involve, we don't want extra rules, right? So you have your product rule that you identified, x e to the x, good. And all of that is buried inside the tangent. So what's the main derivative rule for the problem?
Tangent.
Tangent is not derivative rule, it's a function. Derivative rules are chain rule, product rule, quotient rule. Those are derivative rules. We have to cover implicit differentiation logarithms.
Product rule.
The chain is main and then product is buried inside. So the difference between the two problems, I have to now bring them both here. So the top problem has the product rule as a main rule and chain was buried inside. The one on the bottom has a chain rule as a main derivative rule and product is buried inside. So these two problems have the same rules but in the opposite order. And you just have to figure out, right, which rule is the rule that goes first, which is the rule that applies to the whole problem, and which is the rule that applies locally to a part of the problem. So you can see over here that you can have two separate functions multiplied, so that's a product rule for the whole problem. Over here, tangent applies to everything, which is why the chain rule is the boss. So to do the chain rule, the derivative of tangent is secant squared of the same e to the x inside, and then we multiply by the derivative of inside, which is when the product rule kicks in. Copy the first, derivative of the second, plus copy the second, derivative of the first. So now this becomes secant squared of x e to the x times, and over here we can kick out e to the x and have x plus 1. So, factored out, e to the x plus 1, secant squared x e to the x. So for this particular problem, chain rule was applied to the entire problem, and the product rule was within the chain. So once we had to differentiate what I call the guts, right? Once I had to differentiate this, well, that's where the product rule kicks in, because that is the product rule. Function x times the function e to the x. So that was the product rule. And then we'll simplify it, get it ready for chapter 4, so that we can do the rest of the problem. Cool, huh? No? Yes? Let's see what else we can figure out. Square root of x squared plus 1 divided by sine x. So this one is going to be different, right?
Yeah.
What do we see immediately for this problem?
You have the square root right there. That's your primary. And then you're going to go.
Excellent. Square root is the primary, which means that's what rule is the primary rule?
Product rule.
We don't have a product rule. It's the quotient and chain. Okay, so quotient and chain rule are two rules that are important in this problem. Now, which one is the one for the whole problem and which one is part?
Chain first, then quotient.
Chain, yes. So chain is the main because everything is stuffed into the same square root. So chain is the main, and then when you have to take the derivative of the inside, well, then the quotient rule kicks in. I try it, see how it goes. No pressure, we have 18 seconds. let's take a look. So the square root we can rewrite as exponent of 1/2. And we treat this problem as x to the 1/2. So we know that the derivative of that would be 1/2 times x to the negative 1/2, but x is actually x squared plus 1 over sine x. And then we follow with the chain, which is the derivative of the inside, which is when the quotient rule kicks in. So you have your sine squared in the denominator, you have your sine x times the derivative of the top is 2x minus, copy the numerator, which is this one, times derivative of the sine is cosine x. And now we fix this the best we can. We have two sine squared x times the square root of x squared plus 1 over sine x. And in the numerator we have 2x sine x minus x squared plus 1 times cosine x. And now we can flex a little bit further, because I can steal one of the signs and then stuff it under the square root. It will become sine squared and it would cancel the one in the denominator. So at least we don't have double fraction. So take this sign, write it as sine x times sine x, and then take this sign and stuff it inside to become, I want to put the arrow somewhere else. So take then this sign and stuff it in the root. So the problem now is 2x sine x minus x squared plus 1 cosine x, 2 sine x, and inside the square root you will just have x squared plus 1 times sine x. Because one of the signs would cancel. Why? It's when you stuff something into the square root, it becomes squared. So you would have two of the signs in the numerator and one would cancel with the denominator. So this would be the simplified version. It can go further, but yeah, it's good enough.
We're not bothering rationalizing right now.
Never. Because when you set this equal to 0 in chapter 4 and you cross multiply, denominator always dies completely. We didn't even have to bother getting the double fraction out of it. Like we could have left it right here. It would be fine for purposes of chapter 4. But you can make it a little bit cosmetically better, you do it, right? When it's easy to make it cosmetically better. But to rationalize this, it would actually make it worse, because then you would have to deal with that stuff later when you set it equal to 0. So if you have square roots in the denominator, in terms of functions, you don't leave numbers under the roots, right? So you don't leave a square root of 2 in denominator, because you can't divide by that, right? Division is about making piles, and piles have to be the finite number. And the square root of 2 is not a finite number, it's irrational, which is why we don't like them in the denominator. But the square root of this mess, x could be 0. If x is 0, well, it can't because of this sine x. But if x is 0 in this case, then the whole thing under the square root is 1, and square root of 1 is 1, so no harm done. So for some values of x it will be rational, for some values of x would be irrational, and we don't have to preemptively, right, rationalize it for all values, because some values are going to work out nicely. So when you have functions, it is okay to leave the square root, especially if you know that down the line, right, your problems will transform in such a way where you set it equal to 0. And I mentioned that a couple of times. And then that 0 would kill the denominator completely. So actually any work done in the denominator is just a complete waste of time, because it will be annihilated by the 0 every single time. All right, let's see something else. The derivative of, what should we have? X cubed cosine x divided by x squared plus 1. Try that. What are the rules? Product and quotient. Anyone else?
Product, quotient, and chain.
Where's the chain? Just product and quotient, yes. It was a trap. Here, I'll write it in blood. No chain here. So the main rule is quotient, and then when you have to do the derivative of the top, you do the product rule. So x squared plus 1 squared, x squared plus 1 times the derivative of the top. This is where the product rule kicks in. Copy the first times the derivative of the second plus copy the second times derivative of the first minus x cubed cosine x times the derivative of the denominator is 2x. Awesome. All we need to do is to simplify this a little bit and we're done. Again, we're not bothering with the denominator because in chapter 4 it is going to die, so we don't care. We'll just fix as much as we can in the numerator. So we have our x squared plus 1, and then we have 3x squared cosine x minus x cubed sine x. I swapped the order so I can put the positive term first and then the negative. Then I have minus 2x to the 4 cosine x. So I could technically factor out x squared because all three terms have x squared, but there is no x squared to cancel with in denominator, so we'll just leave it here. So a lot of cool stuff, right? Another one? Say no more. d dt of cosine cube t divided by secant squared t.
Cool.
what do we have here? Okay. Me neither. I had 4.5 hours of sleep. I'm charged too. I'm buzzing all day. Plus, I had like 6 Kit Kat bars. So I am high on sugar. I'd run a marathon now. It's raining, so. What mood? Mood is awesome.
I said no, it is like when it rains, it's like slower.
Not everyone.
That's just because you're high on sugar.
Exactly. You have to compensate.
Overdose.
What should we do here? Come on. You can do it. We can help, Home Depot.
Top 3 cosine t.
It's cosine raised to the 3rd power. So in parentheses. No, that's for LNs only. Oh, you mean to take the derivative? Well, we can because there is a division. You can't just take the derivatives separately. So the obvious thing is the quotient rule, right?
Yeah.
That's the obvious thing. But that's not the easiest thing, because if you use basic trig identities, you get to kill the quotient rule.
Oh.
Secant is 1 over cosine, right? So this is the same as the derivative of cosine to the 5t. Oops. So it's cheap. 5 cosine 4t times negative sine t in a chain rule for negative 5 sine t cosine to the 4t, and we're done. This is why trig is so awesome. It can go around some of these problems.
To realize that by just looking at it, unless you're dumb for a long time.
Which is why practice is crucial. You do problems until you start bleeding under the fingernails, and then you just do one more problem afterwards, and that's it. You're done for the day. Let's see if I can find one more example from the book directly, and we are done with chain rule. Hopefully you guys will work on exercise. So now we're just going to lift something directly. Give me a number 57 to 68. 61. d theta of theta squared secant 5 theta. So this is now the old edition of the book, so it doesn't match the new numbers. Doesn't matter. So there is a problem. Have fun. So what's the rule? Product rule. Good. So copy the first. Derivative of the second. What's the derivative of secant? Secant
X
tangent. Good. So tangent. And then we have to multiply by the chain, which is 5. Good. And then we have plus, copy the second, which is secant 5 theta, times the derivative of the first, which is 2 theta. We can kick out what? Theta secant. Okay, theta secant 5 theta. And what's left inside is 5 theta tangent 5 theta plus 2. There we go. All right. So that's the chain rule. Way to take the derivative of the function composition. Where's the formula? Holy nightmare. There we go. Or the chain rule, we take the derivative of the outer function with the inner one plugged in, and then we take the derivative of the inner function. And if we have multiple levels, then we work it out as a chain, which is shown here. The number of functions you have is the number of derivatives that you need to have in your answer. So we'll take a break, about 300 seconds or whatever. Then when you come back, the implicit differentiation.